Hello, and welcome to Sleepy Wiki. Gently allow your shoulders to drop and let your breath soften as we prepare for a tranquil journey together. Tonight, our gentle whisper will guide us through something profoundly ancient, endlessly mysterious, and utterly vital, yet entirely unseen. Imagine, if you will, the subtle sculptor of mountains, the quiet carrier of distant scents, the unseen hand that rustles the leaves of ancient trees. It is a force that has woven itself into every corner of our world, from the deepest canyons to the highest peaks, from the vast, open ocean to the smallest garden. We'll drift with the very breath of the world, exploring the quiet narrative of the air in motion, feeling its presence without ever quite grasping it. Consider the silent journeys it makes, the stories it witnesses, from the first dawn to the settling dusk, always moving, always changing, yet always just there. It's a phenomenon as old as time itself, a constant companion to life on Earth. If these quiet journeys bring you comfort and help you unwind, a gentle tap on the like button or a soft subscribe is always appreciated, helping more tired minds find their way to our peaceful corner of the internet. Join me now as we softly explore the elusive beauty of the wind. Let's begin our journey by uncovering where wind truly comes from. As you snuggle deeper into your blankets tonight, imagine another, much larger blanket wrapped around our entire planet. It's an invisible one, made of countless tiny air molecules constantly swirling and dancing. This is our atmosphere, a comforting embrace that allows life to flourish. You can't see it, or perhaps even consciously feel it, but it's always there, a profound and essential presence. Now, even though we can't see this atmospheric blanket, it has weight. Imagine an enormous, feathery duvet, so vast it covers continents. Just like anything with substance, it presses down on everything beneath it, on your roof, on the trees, on the very ground you sleep above. This gentle, constant pressing is what we call atmospheric pressure. It's the collective force of all those air molecules above a particular point, drawn down by Earth's steady gravity. But here's a curious thing, my dear listener. This pressure isn't always perfectly even everywhere. Sometimes the blanket feels a little heavier in one spot, pushing down with a bit more force, while in another it might feel lighter, like the duvet has been lifted just a touch. These subtle differences, these invisible hills and valleys of pressure across our world, are the very whispers that stir the wind into being. They are the unseen forces that begin the grand ballet of moving air. What causes these variations? Mostly, it's our magnificent sun, that distant golden lamp that bathes our Earth in warmth. Think of it like a giant baker, carefully browning a vast, uneven cake. Some parts of the cake, perhaps a dark patch of land like a sun-baked desert or a paved city street, might absorb more heat and warm up quickly. Other parts, like a cool, reflective ocean or a snow-capped mountain range, might stay cooler for longer or even reflect much of the sun's energy away. This uneven heating is the first crucial ingredient in our wind-making recipe. When the sun's rays warm the ground, that warmth doesn't stay put. It rises, gently coaxing the air directly above it to warm up too. The ground acts like a giant, silent radiator, transferring its heat to the lowest layer of the atmosphere. Now, warm air, like a carefree balloon suddenly lightened of its ballast, becomes less dense. Imagine a crowded room where everyone suddenly feels too hot. They might spread out a little, finding more space for themselves. That's what air molecules do when they heat up. They vibrate more vigorously, move faster, and spread further apart. And when they spread out, they take up more room while maintaining the same mass, thus becoming lighter, less weighty for their volume. This lighter, warmer air begins to rise, drifting upwards, like a warm breath exhaling into the cool night sky. This process is called convection. As this column of air ascends, it essentially lifts some of the weight off the surface below it. It leaves behind a subtle void, a place where the total weight of the air pressing down on the surface is now a little less. We call this a low-pressure area, a gentle dip or depression in our atmospheric blanket, where the air feels less heavy, less insistent in its downward push. Conversely, where the ground or water remains cooler, perhaps over a vast, chilly ocean or a region of dense forests that absorb less heat, the air above it doesn't have that same urge to rise. In fact, cold air is quite the opposite. Think of those same friends, shivering a little, huddling closer together for warmth. Cold air molecules are denser, they move slower and pack more tightly together. They feel heavier, more substantial, more compact. This denser, cooler air naturally sinks, settling down towards the Earth's surface like a heavy sigh, adding its mass to the air already present. As it descends, it adds its weight to the air already there, increasing the pressure on the surface. This is what we call a high-pressure area, a gentle hill or rise in our atmospheric blanket, where the air presses down with a little more force, a little more authority. So now we have these invisible hills of high pressure and valleys of low pressure scattered across our world. And nature, my dear one, has an extraordinary tendency to seek balance, to smooth things out, to equalize differences. It doesn't like extremes. Imagine a gentle slope on a playground, with children gathered densely at the top, representing high pressure, and fewer, more spread out children at the bottom, representing low pressure. What naturally happens? The children at the top will gravitate towards the bottom, seeking to even out the distribution, drawn by the open space. In the atmosphere, this urge to equalize is incredibly powerful and constant. The air from those areas of higher pressure, where it's feeling a bit crowded and heavy, will begin to move. It will gently, or sometimes not so gently, push its way towards those areas of lower pressure, where there's less resistance, more room, and a natural vacuum to fill. This invisible push, this difference in pressure over a distance, is what scientists call the pressure gradient force. It's the fundamental engine that drives all wind. And this movement, this flow of air from high pressure to low pressure, is quite simply wind. That's its beginning, its very genesis. Whether it's the faintest whisper rustling leaves outside your window or a mighty gale sweeping across the ocean, it all starts with this fundamental principle. Air always seeks to flow from where it's pressing down more heavily to where it's pressing down less heavily, from the hills to the valleys of atmospheric pressure. Now, the steepness of this pressure slope matters enormously to the character of the wind. If the difference between a high-pressure hill and a low-pressure valley is very gradual, like a gently sloping meadow, the air will move slowly, producing only a soft breeze. The pressure gradient is shallow, and the force is mild. The air takes its time to equalize. But if that pressure difference is very dramatic, like a sudden, steep cliff face plunging into a deep ravine, the air will rush down with great urgency and power. The pressure gradient is steep, and the force is strong. This is why some winds are fierce and others are barely noticeable. The closer those high and low pressure zones are to each other, the more intense the pressure gradient, and the faster and stronger the wind will blow. Meteorologists, the scientists who study our weather, have a clever way of visualizing these pressure hills and valleys across vast distances. They draw invisible lines on maps called isobars. These are lines that connect points of equal atmospheric pressure, much like contour lines on a topographical map show the elevation of the land. When isobars are drawn close together, it means there's a steep pressure gradient, indicating the presence of strong winds. When they're spaced far apart, it means a gentle gradient and calmer, more tranquil air. So, as you drift towards sleep, remember the silent drama unfolding high above and all around us. The sun's warmth shaping invisible hills and valleys of air pressure, and the atmosphere's constant desire for balance, pushing air from the heavy to the light, creating every single breath of wind we feel. It's a beautiful, intricate dance, orchestrating the very air we breathe, from the gentlest sigh to the most powerful gust. This fundamental movement, this journey from high to low pressure, is the very heart of wind's existence. But the story of wind isn't quite complete with just this initial push. There are other fascinating forces at play, like invisible dancers twirling and deflecting the wind from its straight path. The Earth's own majestic spin, for example, adds a curious twist, gently nudging our moving air currents into magnificent curves and swirls. We'll explore that intriguing effect, the graceful Coriolis force, as we continue our journey into the wonders of our planet's breathing, and discover how it shapes the grand patterns of wind across our world. Now that we understand wind's origin, let's see how these invisible currents organize themselves across our planet. Imagine, if you will, that our Earth is not just a silent spinning sphere, but a living, breathing entity, constantly inhaling and exhaling. These breaths, these currents of air, are what we call wind. But just like our own breath changes, sometimes a deep, steady sigh, other times a quick, gentle whisper, the winds of our world are wonderfully varied. Some are grand, sweeping pronouncements, while others are intimate, whispered secrets unique to a specific place. It's a beautiful, intricate dance of air, constantly unfolding above and around us. First, we turn our attention to the vast, majestic movements, the Earth's grand symphony, orchestrated on a truly global scale. These are the global wind systems, the planet's deep, rhythmic respirations, driven by the very heart of our sun. Imagine the sun as a distant painter, its golden warmth not spread evenly across the Earth's canvas. The areas around the equator receive direct, intense warmth, like a cozy blanket pulled snugly around the middle of our planet. This warmth causes the air there to become light and buoyant, gently rising into the sky. As this warm, light air rises, it begins a slow, majestic journey towards the poles. But the Earth, ever the graceful dancer, is constantly spinning. This spin introduces a remarkable phenomenon known as the Coriolis effect. Picture a tiny ant trying to walk in a straight line across a spinning record player. Its path would appear to curve. Similarly, as vast rivers of air move across our rotating Earth, they don't flow directly. In the Northern Hemisphere, these global winds are gently nudged to the right, while in the Southern Hemisphere, they are softly guided to the left. This elegant twist is fundamental to how our global winds arrange themselves. This grand circulation of air, guided by the sun's warmth and the Earth's spin, can be pictured as three immense, invisible conveyor belts in each hemisphere. These are known as the Hadley cells, Ferrel cells, and polar cells. Closest to the equator, stretching from about 0 to 30 degrees latitude, we find the Hadley cells. Here, the sun's radiant energy warms the air, causing it to rise, creating a zone of low pressure, a gentle atmospheric uplift. As this warm, moist air ascends, it cools and releases its moisture, often forming clouds and bringing life-giving rains to the equatorial regions. Then, high in the atmosphere, this now cooler, drier air flows away from the equator, eventually sinking back down to Earth around 30 degrees latitude, creating zones of high pressure, a calm, settling embrace of air. This sinking air is dry and warm, contributing to many of the world's deserts found at these latitudes. As this air completes its journey and settles back towards the surface, it flows back towards the equator, completing the loop. These surface winds, heading towards the equator, are known as the trade winds, steady and reliable currents. Moving further north or south, between approximately 30 and 60 degrees latitude, lies the more complex Ferrel cell. This cell is like a gear caught between the powerful Hadley and polar cells, driven less directly by temperature differences. In the Ferrel cell, air tends to flow poleward at the surface, driven by the high pressure from the Hadley cell, and then rises around 60 degrees latitude. These surface winds, traveling away from the tropics towards the poles, are what we call the westerlies. They are the prevailing winds that grace many temperate regions, often carrying changing weather patterns. Finally, at the highest latitudes, from about 60 degrees to the poles, we encounter the polar cells. Here, the extremely cold, dense air at the poles sinks, creating a zone of intense high pressure, a heavy, settled stillness. This frigid air then spreads out across the surface, flowing away from the poles towards lower latitudes. As it travels, it eventually warms slightly and rises around 60 degrees latitude. The surface winds flowing away from the poles are known as the polar easterlies. Crisp and cold, carrying the icy breath of the polar caps towards the temperate zones. These vast, invisible river-like flows of air aren't just at the surface. High above us, particularly at the boundaries of these circulation cells, flow incredibly fast currents of air known as jet streams. Imagine them as powerful, meandering rivers high in the sky, thousands of kilometers long and narrow. These swift currents, traveling at speeds that can exceed 200 miles per hour, are like invisible highways for weather systems, guiding storms and influencing temperature patterns far below. They are the dynamic architects of our larger weather events, shifting and shaping the grand patterns we see on our weather maps. So, while these global wind systems provide the grand framework, the sweeping narratives of our planet's breath, the Earth also breathes in smaller, more intimate ways. Stepping down from the global stage, we encounter the delightful intricacies of local wind systems. These are the winds that tell tales of specific places, shaped by the unique contours of the land, the presence of water bodies, or the particular dance of sun and shadow within a valley. They are the whispered secrets of geography. Consider the gentle sigh of the ocean during the day, a phenomenon known as the sea breeze. As the sun climbs high, it warms the land much faster than it warms the vast, shimmering expanse of the sea. The air above the sun-drenched land becomes light and rises, creating a localized area of lower pressure. Over the cooler water, the air remains denser and descends, creating higher pressure. Nature then sends a cooling breath from the sea towards the land, a refreshing sea breeze that often greets coastal dwellers in the afternoon. It's like the ocean, exhaling a cool sigh onto the warm shore. But as the sun sets and twilight descends, this dance elegantly reverses, giving us the land breeze. The land cools down much more rapidly than the ocean, which retains its warmth longer. Now the air above the relatively warmer water becomes buoyant and rises, creating low pressure over the sea, while the air above the cooler land becomes dense and sinks, creating high pressure. And so, a gentle current of air flows from the land out towards the sea, carrying the quiet hush of the night. It's the land's soft evening exhalation. Similar daily rhythms can be found in mountainous regions. During the day, as the sun warms the mountain slopes, the air along these slopes becomes less dense and rises gently up the valley. This is the valley breeze, also called an anabatic wind, literally climbing up wind. It's the mountain's slow upward breath. Conversely, as night falls and the slopes cool rapidly, the air above them becomes denser and heavier. This cool, heavy air then flows silently down into the valley, creating a mountain breeze, or a katabatic wind. Flowing down wind. It's the mountain exhaling a cool, heavy sigh into the valley. And then there are the grand seasonal shifts, like the dramatic monsoons. These demonstrate how immense land masses interact with vast oceans over an entire year. During the summer, a continent might heat up intensely, drawing moist, cool air from the adjacent ocean towards it, bringing heavy, life-giving rains. It's like the continent's deep, thirsty inhale of humid air. In winter, the continent cools rapidly, becoming much colder than the ocean, and the winds reverse, blowing dry, cool air from the land out to sea. This is the continent's long, dry exhale. These seasonal winds shape cultures, agriculture, and entire ecosystems. And every gust, every whisper of wind, whether it's a global current shaping continents or a local breeze rustling leaves in your backyard, is part of this continuous, intricate system. They are all facets of our planet's beautiful, dynamic atmosphere, a testament to the elegant physics at play all around us. And with that understanding of the grand classifications, perhaps we can gently drift towards a deeper appreciation of the invisible forces that choreograph this elegant dance, the fundamental laws that guide every breath of wind across our world. Now let's peek behind the curtain to discover what truly governs these vast, invisible currents. The wind might seem like a whimsical spirit, a spontaneous breath of the planet, but in truth, it is a masterful dancer, guided by a set of ancient, unyielding laws. Tonight, let's peek behind the curtain and discover the invisible choreographers that govern every swirling gust and gentle breeze. Our story of wind begins with a fundamental truth. The air around us, invisible as it is, has weight. It presses down on everything, creating what we call atmospheric pressure. Think of it like a colossal, invisible blanket draped over the earth. This blanket isn't perfectly even. Some parts are a little thicker or heavier than others, leading to areas of high pressure, while other regions are thinner or lighter, forming areas of low pressure. This subtle difference is the very first whisper of wind's journey. Imagine two neighboring rooms, separated by an invisible wall. One room is densely packed with sleepy clouds, pressing gently outward. That's our high-pressure zone. The other room is spacious and inviting, a low-pressure zone. Nature, in its wisdom, abhors imbalance. So, just as water flows downhill, or a crowded room naturally empties into a less crowded one, air yearns to move from where it's more concentrated to where it's less so. This yearning, this initial push or pull, is what scientists call the pressure gradient force, PGF. It's the primal engine of all wind. The stronger the difference in pressure over a given distance, the steeper the invisible slope between high and low pressure, the more urgently the air rushes to equalize it. You can almost feel its quiet determination. If you could see pressure lines on a map called isobars, you'd notice the PGF always tries to push air directly across them, from a higher value to a lower one, like an arrow pointing straight down a hill. This force alone would send air streaming directly from every high-pressure system straight into every low-pressure system, in the most direct, straightforward path imaginable. But our world is not a static canvas. It's a magnificent, spinning orb. And as the Earth gracefully pirouettes through space, it adds a captivating twist to our wind's journey. As soon as the air begins to move, stirred by the pressure gradient force, it experiences an apparent deflection, an invisible nudge, thanks to the Earth's rotation. This elegant, subtle influence is known as the Coriolis effect. It's not a true force in the sense of a direct push or pull. Rather, it's a consequence of observing motion on a rotating frame of reference. Picture yourself on a colossal, slowly spinning merry-go-round. If you try to roll a ball straight across its surface to a friend opposite you, the ball won't reach them in a straight line. From your perspective on the merry-go-round, it will appear to curve. From an outside, stationary observer, the ball indeed traveled in a straight line, but the merry-go-round moved underneath it. This is exactly what happens with vast air masses. In the northern hemisphere, this invisible nudge gently guides moving air to the right of its intended path. In the southern hemisphere, it artfully deflects it to the left. The Coriolis effect is a true maestro of misdirection. It's strongest at the poles, where the Earth's spin has the most dramatic effect on moving objects, and gradually diminishes to zero at the equator, where the rotational motion is purely horizontal. What's more, its strength is directly proportional to the speed of the wind. Faster winds experience a stronger deflection. Crucially, the Coriolis effect only changes the direction of the wind. It never speeds it up or slows it down. And so, as the pressure gradient force tries to send air rushing straight from high to low, the Coriolis effect begins its graceful deflection. Up high, in the free atmosphere, thousands of feet above the ground, where the wind flows unimpeded, these two forces often find a delicate equilibrium. The air, pushed by the PGF, is simultaneously nudged by the Coriolis effect, leading it to flow parallel to the isobars, rather than across them. This balanced flow is called the geostrophic wind, a beautiful example of nature's elegant mechanics. Imagine two perfectly synchronized dancers, moving in harmony, never quite touching, yet always in step. But our world isn't just a smooth, spinning sphere. It's adorned with majestic mountains, vast forests, bustling cities, and undulating oceans. And these features introduce the next important player in our wind story: friction. Think of friction as the gentle resistance, the slight drag that anything moving across a surface experiences. For wind, friction arises from its contact with the Earth's rough, textured surface. On every tree branch, every building, every ripple on the water creates tiny eddies and disturbances, slowing down the flowing air. This force is most potent closest to the ground, within what we call the planetary boundary layer, typically extending up to about a kilometer or so. As you ascend higher into the atmosphere, the influence of friction rapidly diminishes until the air flows almost entirely free of its grip. Imagine a river flowing over a rocky bed. Near the bottom, the water is turbulent and slow, but further up, it flows more smoothly and swiftly. Friction acts like that unseen resistance, always working to slow the wind's speed. And here's where the intricate dance truly unfolds. Because friction slows the wind, and because the Coriolis effect's strength depends on wind speed, friction effectively weakens the Coriolis deflection. With a diminished Coriolis effect, the pressure gradient force, which remains unaffected, gains a slight advantage. It can now pull the wind more directly towards the lower pressure. So near the surface where friction holds sway, the wind no longer flows perfectly parallel to the isobars. Instead, it crosses them at a gentle angle, always veering towards the low-pressure center. This is why surface winds spiral inward towards low-pressure systems, like cyclones, and spiral outward from high-pressure systems, like anticyclones. It's a subtle but profound alteration, a beautiful compromise orchestrated by these three invisible forces. There's one more subtle player that enters the stage when air flows in a curved path, as it often does around pressure systems: the centrifugal force. While not a true force in itself, it's the apparent outward push you feel when you're spinning in a circle, like being pressed against the side of a car as it takes a sharp turn. When air curves around a low or high pressure system, the centrifugal force provides an outward push, creating a slightly more complex balance with the PGF and Coriolis, resulting in what's known as a gradient wind. This allows for the grand, sweeping spirals of weather systems we see from space. So our wind is not simply air moving, it is a magnificent, ongoing negotiation. the relentless push of the pressure gradient force, the elegant deflection of the Coriolis effect, the grounding resistance of friction, and the subtle outward pull of centrifugal force, they all intertwine in a constant dynamic ballet. They conspire and collaborate, creating the gentle whispers and powerful roars that shape our weather and define the very breath of our planet. These forces are not just abstract concepts. They are the unseen engineers designing every gentle rustle of leaves and every towering storm. They are the reason our world experiences such diverse and intricate weather patterns, from the trade winds to the roaring westerlies. And understanding their interplay is like glimpsing the secret language of the atmosphere. With this understanding of the forces that guide the wind, perhaps you can now sense how these principles create something truly magnificent high above us, rivers of air moving at breathtaking speeds. Let's lift our gaze now, far beyond the familiar clouds that scud across our skies, to discover the fastest winds our planet knows. Imagine ascending gently, softly, past the tallest mountains, through the realm where airplanes glide, and into the thin, crisp air of the upper atmosphere. Here, the winds tell a different story, a grander, swifter tale, often unseen but profoundly influential. At these lofty altitudes, roughly between 7 and 12 kilometers, about 23,000 to 39,000 feet above the Earth's surface, in a boundary layer we call the tropopause, the very top of our weather-making troposphere, there exist magnificent ribbons of incredibly fast-moving air. These are the jet streams. Think of them as invisible superhighways of wind, encircling our planet, guiding much of the weather we experience down below. They are not merely breezes. These are currents that can flow at speeds often exceeding 160 kilometers per hour, 100 miles per hour, and sometimes even reach a staggering 400 kilometers per hour, 250 miles per hour. Imagine a gentle current, yet powerful enough to carry a tiny whisper around the world in mere days. What gives birth to these sky-high torrents? It's a beautiful dance of fundamental forces. The primary engine behind the jet streams is the stark contrast between warm tropical air and cold polar air. Picture the Earth constantly being warmed by the sun, but unevenly. The equator receives direct, intense sunlight, while the poles receive it at a slant, making them much colder. This creates immense temperature gradients, massive differences in warmth over vast distances. Warm air is less dense and tends to rise, while cold air is denser and sinks. This fundamental difference in air properties sets the stage. As the warm air rises in the tropics and flows poleward, and cold air descends from the poles and tries to flow equatorward, the Coriolis effect steps in. You might remember our whispers about the Coriolis effect earlier, how the Earth's rotation deflects moving objects, including air and water. For these large-scale movements in the upper atmosphere, the Coriolis effect is a game changer. It deflects the air currents, turning them predominantly eastward in both the northern and southern hemispheres. So, what starts as an attempt by the atmosphere to equalize temperature differences becomes channeled into these powerful eastward-flowing currents, our incredible jet streams. There are two main types of jet streams we often talk about: the term polar jet stream and the subtropical jet stream. The polar jet is usually stronger and sits closer to the poles, marking the boundary between the frigid polar air and the milder air further south. The subtropical jet is higher up and generally weaker, separating the tropical air from the mid-latitude air. Both are vital conductors in the grand orchestra of our planet's climate. But these aerial rivers are not straight, unwavering lines. Oh no, they meander and twist like great invisible rivers flowing through the sky. These large wave-like patterns are known as Rossby waves or planetary waves, and they are crucial to our weather. Imagine a giant undulating serpent moving across the globe. When a jet stream dips south, it forms a trough, pulling cold polar air towards the equator. When it bulges north, it creates a ridge, bringing warm tropical air further poleward. These troughs and ridges steer our storm systems, determine where cold snaps will hit, and dictate where warmth will linger. They are the unseen hands that guide the weather patterns we experience day to day, from gentle rain showers to powerful blizzards. For us down below, these jet streams have profound implications. For men, aviation. They are both a blessing and a challenge. Pilots learn to ride the tailwinds of the jet stream when traveling eastward, significantly cutting down on flight times and fuel consumption, letting the powerful currents give their aircraft a gentle yet mighty push. But when heading westward, they must often navigate to avoid the full force of a headwind, choosing different altitudes or routes to conserve energy and keep the journey smooth. Beyond the jet streams, the upper atmosphere holds other fascinating secrets and phenomena. Higher up in the stratosphere, gentle winds also blow, driven by different thermal patterns and energy absorption. But perhaps one of the most talked about upper atmospheric phenomena in recent years is the polar vortex. This isn't strictly a jet stream, but it's intimately connected. The polar vortex is a massive area of low pressure and swirling cold air that normally sits stably over the Earth's north and south poles, contained by strong westerly winds in the stratosphere. When these containing winds weaken, the vortex can become disrupted, allowing segments of that intensely cold polar air to spill out and descend to lower latitudes, bringing with it those dramatic cold snaps we sometimes feel in winter. And then, as we ascend even further into the very edges of space, where the atmosphere grows incredibly thin, another breathtaking phenomenon lights up the night sky: the aurora borealis in the north and the aurora australis in the south. While not a wind phenomenon itself, it's a spectacular interaction occurring in our upper atmosphere, primarily in the thermosphere. At altitudes much higher than even the jet streams. These shimmering, dancing lights of green, pink, and purple are created when charged particles from the sun, carried by the solar wind, collide with gases in our Earth's magnetic field. Each gentle flicker is a tiny scientific event, a cosmic ballet playing out high above us, reminding us of the invisible forces at play around our sleeping planet. So, from the swift unseen highways of the jet streams to the swirling cold of the polar vortex and the dancing lights of the aurora, the upper atmosphere is a realm of incredible dynamism and beauty. It reminds us that wind, in all its forms, is an intricate global force, yet constantly shaping our world, often in ways we don't immediately perceive, but which influence everything from the flight of an airplane to the chill in the winter air. And these great aerial currents ultimately touch everything below, sculpting the very weather and climate we experience each day. Let us turn our thoughts now to the profound influence of wind on the grand, intricate systems of our weather and climate. The Earth itself is a magnificent living orchestra, and the wind, its tireless conductor, orchestrating a symphony of warmth, moisture, and movement that shapes every corner of our world. At its very core, wind is our planet's great equalizer, a gentle hand striving to balance the sun's generous yet uneven distribution of warmth. Think of the sun as a cosmic spotlight, shining most intensely upon the Earth's equator, leaving the poles in a cooler, dimmer glow. This difference in temperature creates a colossal pressure imbalance. Warmer air near the equator, being lighter, rises, creating areas of low pressure, while colder, denser air near the poles sinks, forming high-pressure zones. The wind, in its eternal quest for equilibrium, flows from these areas of high pressure to those of low pressure, acting as a colossal, invisible conveyor belt. It tirelessly carries the sun's stored heat from the vibrant, sun-drenched tropics towards the cooler, more tranquil polar regions, and likewise colder air ventures towards the equator. Without this constant atmospheric redistribution, the tropics would become unbearably hot and the poles impossibly frigid, transforming our diverse planet into extremes of uninhabitable landscapes. It is this gentle, ceaseless movement that tempers our climates, creating the very conditions for life to flourish across varied latitudes. But the wind's role extends far beyond merely ferrying warmth. It is also the Earth's most diligent gardener, an invisible shepherd of moisture. As warm, moisture-laden air rises over oceans and tropical forests, it collects vast quantities of water vapor, transforming it into invisible rivers in the sky. The wind then becomes the current for these atmospheric rivers, carrying them across continents and over mountain ranges. As these moisture-rich air masses ascend, the air cools and the water vapor condenses, blossoming into the soft, billowy clouds we see floating above us. It is the wind that then gently coaxes these clouds to release their precious cargo as rain or snow, nourishing the thirsty land, filling our rivers, and sustaining forests and fields far from their oceanic origins. This continuous cycle, driven by the wind, is the very heartbeat of our global water system, a delicate dance of evaporation, transport, and precipitation that renews life with every breath of air. These vast movements of air, however, are not simply straight lines from one place to another. Our spinning Earth adds an elegant twist, a subtle deflection known as the Coriolis effect. Imagine a child on a merry-go-round trying to roll a ball to another child across from them. The ball appears to curve as the merry-go-round spins. Similarly, the Earth's rotation deflects winds to the right in the northern hemisphere and to the left in the southern hemisphere. This unseen hand of deflection is what transforms simple air currents into the majestic, swirling patterns of our weather systems. It's why low-pressure systems, often associated with stormy weather, spin counterclockwise in the north and clockwise in the south. They are great atmospheric whirlpools, gathering energy and moisture. Conversely, high-pressure systems, which typically bring clear, calm skies, spiral in the opposite direction. These grand atmospheric dances choreographed by the wind and the Earth's rotation, are the direct cause of the daily weather patterns that shape our lives, from a gentle summer breeze to a winter's snowstorm. Furthermore, the wind acts as a boundary maker, shaping the encounters between different air masses. Consider the meeting of warm, moist air and cold, dry air. These are the meteorological fronts that bring about dramatic shifts in weather. When a warmer air mass advances, gently nudged by the wind, over a colder, denser one, we experience a warm front, often bringing steady, widespread precipitation as the warmer air slowly rises and cools. Conversely, when a colder, more assertive air mass pushes into a warmer one, driven by strong winds, we witness a cold front, typically characterized by abrupt temperature drops, sharper rain, and often the dramatic power of thunderstorms. These atmospheric skirmishes, entirely orchestrated by the subtle pressures and relentless movements of wind, are fundamental to the ever-changing tapestry of our daily weather. Yet, the wind's reach extends beyond the visible sky, gently pressing upon the vast expanse of our oceans. Its persistent breath on the water's surface generates the major surface ocean currents, colossal, slow-moving rivers within the sea. The same global wind patterns that distribute heat and moisture in the atmosphere also create the push and pull that drives the mighty Gulf Stream, carrying warm waters from the Gulf of Mexico across the Atlantic to temper the climates of Western Europe. Other wind-driven currents bring cold, nutrient-rich waters to the surface in phenomena like upwelling, nurturing marine ecosystems, and influencing global fisheries. These wind-propelled ocean currents become another critical layer in Earth's complex thermostat, storing and redistributing vast amounts of heat and playing a vital role in long-term climate patterns like the periodic warming and cooling of the Pacific, known as El Niño and La Niña. The wind's influence, therefore, doesn't just skim the surface. It delves into the deep, stirring the very waters of our planet. On a planetary scale, the wind organizes itself into magnificent, enduring patterns known as global circulation cells. These are like vast, invisible rivers of air that flow continuously around our world. We have the Hadley cells, rising at the equator and sinking around 30 degrees latitude, giving us the steady trade winds that once powered sailing ships. Then come the Ferrel cells, forming the temperate westerlies that characterize much of North America and Europe. Finally, the polar cells complete the circuit, driving the frigid polar easterlies. And high above, flowing like colossal, fast-moving ribbons of air, are the jet streams, narrow bands of incredibly strong winds that snake across the globe. These high-altitude highways of air are the ultimate shapers of our daily forecasts, steering weather systems, guiding storms, and determining where warmth or chill will settle for days or weeks at a time. They are the invisible directors of our atmospheric play, dictating the very character of our climate zones, from verdant rainforests and sweeping grasslands to arid deserts, all sculpted by the relentless, purposeful flow of air. From the gentle caress that carries a single seed to its new home, to the majestic force that sculpts global climate zones over millennia, the wind is a fundamental architect of our world. It reminds us that even the most invisible forces can wield the greatest power, a constant soothing breath that shapes the air we breathe, the rain that falls, and the very temperatures that define our landscapes. It is the silent, tireless worker weaving together the atmospheric tapestry of our planet. As we consider this grand, sweeping impact of wind on our weather and climate, we begin to see the wind not just as a force of nature, but as a resource, a gift that humanity has learned to embrace and harness across the ages. The wind, our ancient companion, has always inspired wonder and provided power. For centuries, we've harnessed its invisible strength, from sails carrying explorers across vast oceans to windmills grinding grain. Today, however, our dance with the wind has evolved into something truly magnificent, something that helps power our modern world. Wind energy. Imagine landscapes dotted with towering, elegant structures, their graceful blades sweeping in silent arcs against the sky. These are our modern wind turbines, gentle giants, quietly working to turn the whisper of the breeze into the hum of electricity that lights our homes and powers our lives. And at the heart of this transformation lies incredible ingenuity, a symphony of design and engineering. Each wind turbine is a marvel, designed to capture the wind's kinetic energy, the energy of its motion, and convert it into a usable form. Picture the blades, often 3 of them, slender and tapering, like the wings of a silent bird. They aren't merely pushed by the wind, like a simple paddle wheel. Instead, they are sculpted with an aerodynamic profile, much like an airplane's wing. When the wind flows over these specially curved surfaces, it creates a pressure difference, a phenomenon called lift. This lift, working with the slight push of the wind, causes the blades to rotate. It's a precise and elegant dance between air and engineering, ensuring maximum capture of the wind's power. These majestic blades, often stretching over 70 meters each, are typically crafted from advanced composite materials, a blend of strong yet lightweight fibers like fiberglass or carbon fiber bound together with resins. This makes them durable enough to withstand nature's forces, yet light enough to spin freely. As the blades turn, they rotate a central shaft or rotor, which extends into the nacelle, the sleek enclosed housing perched atop the towering mast. Inside this nacelle, like the brain of the giant, is where the real magic of conversion begins. First, the spinning shaft usually connects to a gearbox. Think of it like the gears on a bicycle. It takes the relatively slow, powerful spin of the enormous blades and increases its speed significantly. This faster rotation then feeds into a generator, an electrical heart that works on the principle of electromagnetic induction. As coils of wire spin within a magnetic field, or vice versa, they induce an electric current. This is the very same principle, albeit on a grander scale, that generates electricity in many power plants. From the generator, the electricity flows down cables inside the tower, ready to be sent onto our grid, a vast network of power lines that delivers energy to where it's needed. There are different kinds of these wind dancers. The most common are horizontal axis wind turbines, or HAWTs, with their blades facing the wind. But some designs are vertical axis wind turbines, or VAWTs, which look a bit like giant egg beaters. While less common, they have advantages, like not needing to pivot to face the wind. And where these giants stand also matters. Onshore wind farms built on land are what we imagine most readily. But increasingly, we look to the vast open spaces of the ocean, building magnificent offshore wind farms. Here, stronger, more consistent winds blow far from human habitation, promising even greater power potential. Now, let's talk about the economics, the financial currents driving this powerful shift. Wind energy wasn't always the economical choice it is today. In its early days, the technology was expensive, and setting up wind farms required significant investment. But over the past few decades, a quiet revolution has taken place. Through continuous innovation, economies of scale, meaning the more we build, the cheaper each unit becomes, and fierce competition, the cost of generating electricity from wind has plummeted. Today, in many parts of the world, wind power is not just competitive with, but often cheaper than, new power plants fueled by coal or even natural gas. This remarkable achievement is often measured by something called the levelized cost of energy, or LCOE, which essentially calculates the total cost of building and operating a power plant over its lifetime, divided by the total energy it produces. Wind has consistently proven its economic muscle in this arena. This isn't just about cheaper electricity. It's about building a whole new industry. Wind energy creates jobs, not just for the engineers and technicians who design and maintain the turbines, but for the manufacturing workers who build components, the construction crews who install them, and the logistical teams who transport these colossal parts. It's a vibrant ecosystem of innovation and employment, contributing to local economies and fostering skilled labor. Of course, integrating wind power into our existing electricity grids presents its own set of fascinating challenges. Unlike a traditional power plant that can generate electricity on demand, wind power is intermittent. It only produces electricity when the wind blows. This natural variability requires smart solutions. Our grids need to become more flexible, more like a finely tuned orchestra, able to balance the fluctuating contributions of wind with other energy sources. This means investing in smart grid technologies that can predict wind patterns, optimize energy flow, and efficiently manage supply and demand. It also means exploring ways to store excess wind energy for when the wind isn't blowing, a crucial piece of the puzzle. Looking ahead, the future of wind power is truly exhilarating, pushing the boundaries of what we thought possible. Imagine turbines growing even larger, their blades sweeping an even greater area, harnessing more power from each gust. Prototypes for future generations of offshore turbines are already being designed to exceed 15 megawatts of capacity, giants that can power entire towns with just one machine. But perhaps one of the most exciting frontiers is the development of floating offshore wind farms. Currently, most offshore turbines are fixed to the seabed, limiting them to relatively shallow waters. Floating platforms, however, can unlock vast new areas of the ocean where the wind is even stronger and more consistent, allowing turbines to be anchored in much deeper waters, like magnificent cities of light gently bobbing on the waves. This technology is still maturing, but its potential is immense, promising to dramatically expand the global reach of wind power. Energy storage is also evolving rapidly to become the perfect partner for wind. Beyond traditional battery banks, scientists are exploring innovative ways to store wind energy, such as converting excess electricity into hydrogen through electrolysis, a process that splits water into hydrogen and oxygen. This green hydrogen can then be stored and used as fuel or converted back into electricity when needed, offering a powerful solution to the intermittency challenge. Artificial intelligence and advanced forecasting are also playing increasingly vital roles, helping us predict wind speeds with greater accuracy and manage the grid more efficiently, seamlessly integrating wind power into our daily lives. While there are considerations, such as the visual impact of turbines in certain landscapes, potential impacts on wildlife, or even the noise they can generate, though modern designs are becoming remarkably quiet, the overall trajectory is clear. Wind power is an indispensable component of our global effort to decarbonize, to reduce our reliance on fossil fuels, and create a cleaner, more sustainable planet for generations to come. It's a testament to human ingenuity, a gentle, powerful embrace of nature's gifts. As these wind-powered dreams continue to unfold, shaping our energy future with their quiet strength, we're reminded that humanity's relationship with wind stretches back far beyond modern turbines, to the very dawn of civilization itself. And now, as we drift deeper into the quiet hum of the night, let's turn our thoughts to the wind, not just as a whisper against your window, but as an ancient, powerful sculptor of human history. Imagine, if you will, a time long, long ago when our ancestors looked up at the vast open sky, feeling the invisible currents brush against their skin. The wind, in its ceaseless dance, was one of the first great forces of nature that humans learned to observe, understand, and eventually to harness. It was more than just moving air. It was a promise, a challenge, a messenger, and an untamed companion. From the very dawn of agriculture, wind played a vital, though often unsung, role. Picture fields of grain harvested under the vast expanse of the sky. After the arduous work of cutting the stalks comes the winnowing, a beautiful age-old practice where grains are tossed into the air. The heavier kernels fall straight down, while the lighter, unwanted chaff is gently carried away by the breeze. This simple act, performed for millennia, is a perfect intuitive demonstration of aerodynamics, long before anyone understood the scientific principles of lift and drag. The wind, in its patient generosity, helped separate sustenance from waste, shaping the very foundation of human civilization, silently aiding in the feeding of villages and growing empires. But the wind's greatest gift to humanity, perhaps, came with a leap of imagination, the first time someone thought to catch that invisible force and use it to move across water. Imagine the sheer audacity, the ingenuity of those early sailors. From crude rafts to simple dugout canoes, the addition of a rudimentary sail must have felt like magic. Suddenly, the impossible became possible. Distances that once seemed insurmountable, rivers that flowed in only one direction, vast seas that separated lands, all could now be traversed. The sail, a simple piece of fabric catching the wind's breath, transformed water travel from a paddle-powered struggle into a graceful, wind-driven ballet. It was a testament to the power of observation, the understanding that this flowing air could exert force, propelling vessels forward, a profound realization that unlocked new frontiers. As the centuries unfurled, sailing technology grew ever more sophisticated. Early square sails were magnificent for catching a following wind, pushing ships steadily forward when the wind blew from behind. But as understanding deepened, so did the sails themselves. The lateen sail, with its triangular shape and ability to pivot, was a revolution. It allowed ships to sail against the wind, not directly into it, but at an angle, by creating lift much like an airplane wing. This technique, called tacking, opened up a whole new realm of navigation, freeing mariners from being entirely at the mercy of the wind's direct bearing. Imagine the freedom, the expanded possibilities as ships learned to dance with the wind, rather than merely being pushed by it. These innovations were driven by a deeper, albeit often practical rather than theoretical, understanding of how air pressure and flow interact with surfaces. This mastery of sail and wind was the engine behind the Age of Exploration, a period when humanity truly began to map its world. But it wasn't just about sails. It was about understanding the great invisible highways of the sky, the global wind patterns. For instance, the white trade winds, a reliable band of easterly winds, sweep across the Earth's tropical and subtropical regions. These winds are formed as air from high-pressure zones near the poles moves towards the low-pressure zone at the equator, then deflects due to the Coriolis effect, the invisible force caused by Earth's rotation. To early mariners, these were the superhighways to the New World, carrying ships reliably westward across the Atlantic. Without them, such long-distance voyages would have been far more perilous, if not impossible. Imagine the quiet confidence of sailors who knew with an almost spiritual certainty that these winds would carry them. Then there were the westerlies, found in the mid-latitudes, blowing from west to east, guiding explorers on their return journeys, or circumnavigating the globe. And, in the Indian Ocean, the powerful and predictable monsoons dictated the rhythm of trade for thousands of years. These seasonal wind reversals, driven by the differential heating of land and sea, created a natural conveyor belt for ships, carrying goods, cultures, and ideas between Africa, Arabia, India, and Southeast Asia. Imagine the anticipation, the timing of entire economies dependent on the subtle shift of these colossal air currents, a grand natural schedule set by the sun and the vast ocean. But the wind could also be a cruel master. Mariners feared the doldrums, a region near the equator characterized by calm, hot weather and sudden, unpredictable squalls. Here, the air often rises rather than blows horizontally, leaving sailing ships stranded for weeks, their sails hanging limply, awaiting a whisper of wind. This equatorial low-pressure zone, where the trade winds converge, was a testament to the wind's fickle nature, a stark reminder of humanity's enduring vulnerability despite its growing mastery. Imagine the oppressive stillness, the endless horizon, the anxiety as supplies dwindled, all because the invisible hand of the wind chose to rest. Beyond sailing, wind found another revolutionary application, the windmill. This ingenious invention, emerging in various forms across Persia, China, and Europe, transformed the kinetic energy of moving air into mechanical power. Imagine the majestic sight of a windmill's arms, slowly turning against the sky, tirelessly grinding grain into flour, or patiently pumping water from the earth. These silent sentinels revolutionized agriculture, allowing communities to process food more efficiently and irrigate arid lands, shaping landscapes and supporting population growth. They were early, towering examples of clean energy, a testament to human ingenuity in harnessing nature's abundant, renewable forces for daily survival and progress. And culturally, the wind weaves through the very fabric of human expression. In ancient mythologies, wind was often personified as a deity, Aeolus, the keeper of the winds in Greek mythology, Vayu, the Hindu god of wind, Boreas, the fierce north wind. It was a spirit, a breath, a powerful force that could bring blessings or destruction. From the whisper of wind chimes, creating ethereal melodies from air currents, to the mournful sigh of an Aeolian harp, strummed by the invisible breeze, wind has inspired countless poets, musicians, and artists. It features in proverbs, symbolizing freedom, change, or the ephemeral nature of life itself. The very architecture of our homes has often been subtly influenced by wind, with buildings oriented to take advantage of natural ventilation or designed with windbreaks to shelter from harsh gales. So, as we settle deeper into this quiet moment, remember how deeply intertwined our story is with the winds. From helping us farm our food and sail our oceans to powering our mills and inspiring our imaginations, the wind has been an invisible yet utterly essential partner in the grand human journey, guiding us, challenging us, and breathing life into our world in countless, remarkable ways. And to navigate this relationship, humanity has developed ever more refined ways to listen to the wind's whispers, to understand its patterns, and even to glimpse its future. We've journeyed through the unseen currents of our world, understanding the wind's incredible power to shape our lives. But how do we truly listen to the wind? How do we predict its whispers and roars? It's a delicate dance of observation and sophisticated science, a testament to humanity's gentle curiosity about the very air we breathe. Imagine, for a moment, that the wind is a grand, invisible storyteller, constantly sketching its tales across the sky. To understand these stories, we need a special kind of literacy, a way to read the subtle clues it leaves behind. This is where meteorological measurement begins, a patient, precise art of gathering the wind's secrets. On the rooftops of buildings, atop lonely poles in wide-open fields, you might see small, unassuming devices. One perhaps has 3 or 4 little cups spinning gracefully, like miniature dancers twirling in the breeze. This is a cup anemometer, one of the simplest and most enduring instruments for measuring wind speed. Each rotation tells us how fast the air is moving, how quickly the wind is breathing across the land. It's a direct mechanical ballet with the air itself, translating invisible energy into visible motion. Another might look like a tiny airplane propeller, oriented into the wind's flow. Its spins also meticulously counted to gauge the wind's velocity. For even greater precision, especially in research or for specialized applications like wind energy, we use sonic anemometers. These instruments are silent, emitting tiny sound waves, and listening for how the wind distorts their journey. It's like whispering into the wind and hearing its echo tell you how fast it's rushing by, capable of detecting even the most subtle fleeting gusts with incredible accuracy. But speed is only half the story. The wind also has a direction, a point of origin. For this, we look to the wind vane, often a charming arrow or a stylized rooster perched high above. This patient sentinel aligns itself with the wind's source, silently pointing to where the breeze has come from. It's a simple, elegant compass of the sky, guiding us to understand the wind's journey across the landscape, whether it's a refreshing northerly breath or a warm southerly sigh. These surface measurements are just the beginning. The atmosphere is a vast three-dimensional ocean, and the wind doesn't behave uniformly from the ground to the heavens. To truly comprehend its movements, we must send out explorers. Imagine small, silent weather balloons ascending into the deepening twilight. These humble adventurers, carrying a small package of sensors known as a radiosonde, become the wind's own emissaries. As they rise, carried aloft by the very air they seek to understand, they measure a symphony of atmospheric properties: temperature, humidity, and atmospheric pressure at various altitudes. Crucially, by tracking the balloon's path with radar or GPS, meteorologists can determine the wind speed and direction high up in the atmosphere. These are invaluable pieces of information, revealing the invisible rivers of air that flow far above us, shaping the weather systems that arrive at our doorsteps days later. High above the clouds, even more distant observers lend their eyes to the task. Weather satellites, those silent sentinels orbiting our planet, offer a breathtaking panoramic view. They don't directly measure wind speed at the surface in the same way an anemometer does, but they track the movement of clouds, especially the majestic swirls of hurricanes and storm systems. By watching how these atmospheric patterns evolve and drift across continents, scientists can infer the large-scale wind patterns, the grand maestros conducting the Earth's atmospheric orchestra from afar. It's like watching a cosmic ballet unfold and understanding the unseen forces that choreograph each graceful turn. Closer to the ground, but still scanning the vastness, are Doppler radars. These powerful instruments send out pulses of electromagnetic energy and listen for the echoes reflected by precipitation, raindrops, snowflakes, even dust particles. The beauty of Doppler technology lies in its ability to detect the shift in these echoes, much like the changing pitch of a siren as it passes you. This shift, known as the Doppler effect, reveals whether the rain is moving towards or away from the radar and how fast. This allows us to map out the wind fields within storms, pinpointing dangerous wind shear, sudden changes in wind speed or direction over short distances, and understanding the circulation within powerful systems like tornadoes. It's like listening to the voice of the storm itself, deciphering its intentions. And for the most precise, almost surgical understanding of wind, especially for the placement and operation of wind turbines, we turn to LIDAR, light detection and ranging. LIDAR systems use pulsed laser light, much like radar uses radio waves. These laser beams bounce off tiny dust particles and aerosols in the air, and by analyzing the reflected light, LIDAR can create incredibly detailed three-dimensional maps of wind speed and direction, often hundreds of meters up from the ground. It's like gently touching the wind with light, feeling its texture and flow with exquisite sensitivity. And all these disparate threads of information, from the spinning cups on a pole to the laser beams in the sky, from the tiny radio sondes to the orbiting satellites, are meticulously gathered and woven together. They form a comprehensive snapshot of the atmosphere at a specific moment in time. But these measurements are not an end in themselves. They are the crucial initial conditions for the profound challenge of wind forecasting. Imagine trying to predict the exact path of a feather released into a complex, swirling current. That's a simplified analogy for the intricate task of forecasting the wind. This is where the power of numerical weather prediction, NWP models, comes into play. These are not crystal balls, but rather immense, sophisticated computer simulations built upon the fundamental laws of physics, fluid dynamics, thermodynamics, and atmospheric chemistry. Billions upon billions of calculations are performed, essentially projecting the future state of the atmosphere based on its current observed state. The atmosphere is divided into a three-dimensional grid, and at each point in this grid, the model calculates how the wind, temperature, pressure, and moisture will change over time, minute by minute, hour by hour. These models incorporate critical atmospheric principles. For example, the wind is fundamentally driven by atmospheric pressure gradients. It always flows from areas of high pressure to areas of low pressure, much like water flowing downhill. The steeper the pressure hill, the stronger the wind. As the Earth spins, this motion is further influenced by the Coriolis effect, a subtle but profound force that deflects winds and ocean currents to the right in the northern hemisphere and to the left in the southern hemisphere. It's like a gentle, invisible hand guiding the wind's path, giving it a characteristic curve rather than a straight line. Forecasters also closely track fronts, which are the boundaries where different air masses meet. Warm fronts, cold fronts, occluded fronts. These interfaces are often zones of significant wind shifts and changes in weather. They study the mighty jet streams, high-altitude rivers of fast-moving air that can steer entire weather systems across continents, like invisible highways in the sky. And they account for local factors. Mountains that channel wind into valleys, creating powerful gusts, or the daily rhythm of land and sea breezes along coastlines, where the differential heating between land and water creates predictable patterns of air movement. No single model is perfect, and the atmosphere is inherently chaotic, meaning tiny, unmeasurable variations can lead to vastly different outcomes over time. To account for this uncertainty, forecasters often use ensemble forecasting. This involves running the same NWP model multiple times, each with slightly varied initial conditions. Imagine a choir of predictions, each singing a slightly different tune, but together giving a more complete picture of the potential range of future wind scenarios. This helps to identify the most likely outcomes and the degree of confidence in a forecast, allowing for more robust decision-making in aviation, shipping, wind energy production, and even agriculture, where wind can be a friend or a foe. So, as we drift toward slumber, consider the immense effort and ingenuity that goes into understanding and predicting the wind. From tiny spinning cups to advanced supercomputers, humanity strives to listen intently to the Earth's breath, not just for scientific curiosity, but to navigate our world more safely, more sustainably, and with greater harmony. And as we understand the wind better, we also begin to notice something profound. The patterns themselves are changing. We find ourselves at a crucial juncture, a moment when the very breath of our planet seems to be subtly, yet profoundly, changing its rhythm. Imagine, if you will, our Earth as a vast ancient sleeper gently turning in its cosmic cradle. Its atmosphere, a delicate blanket of air, moves in response to the warmth of the sun, just as your own body has a circulation system, blood carrying warmth and nutrients to every part. Our Earth has an atmospheric circulation system. This grand design of global wind patterns is like a magnificent invisible engine, constantly working to distribute heat from the sun-drenched equator towards the cooler poles, striving for a gentle balance across the globe. Without it, the tropics would be unbearably hot and the poles frozen solid. It's a testament to nature's incredible engineering. These global winds aren't random gusts, but part of immense predictable loops, often called atmospheric cells. Think of them as giant, invisible conveyor belts in the sky. Nearest the equator, we have the Hadley cells. Here, warm, moist air rises like a sleepy sigh, carrying its warmth high into the atmosphere before drifting poleward and eventually sinking back down around 30 degrees latitude. This descending air is dry and warm, creating many of the world's great deserts. Then, at the surface, this air flows back towards the equator, creating the gentle, steady trade winds, which sailors once relied upon for their journeys across vast oceans. Beyond these, in the mid-latitudes, are the ferrule cells, a more complex dance influenced by the larger Hadley and polar cells. Here, winds tend to blow from west to east, the westerlies, bringing our familiar temperate weather systems. And finally, at the very top and bottom of our world, are the polar cells, where icy air sinks at the poles, flows towards the mid-latitudes, and then rises again around 60 degrees latitude. Each of these cells, a fundamental component of Earth's breathing, is also influenced by the Coriolis effect, the subtle twist imparted by our planet's stately rotation. This spin is what deflects moving air, turning winds into their characteristic directions, the easterly trade winds, the westerly westerlies, giving them their elegant curved paths across continents and oceans. And then, high above these vast, slow-moving cells, like swift, invisible rivers winding through the sky, are the jet streams. These narrow bands of fast-flowing air, miles above the surface, are the true conductors of our daily weather. They're formed by the sharp temperature differences between large air masses, particularly between the cold air over the poles and the warmer air closer to the equator. Imagine a boundary where two vast, invisible oceans of air meet, one warm, one cold. The jet stream flows along this boundary, guiding storm systems and weather fronts, acting as a kind of atmospheric shepherd for our planet's moods. Now, here is where our story takes a turn as we introduce a new element into this ancient, delicate dance, the warming touch of our changing climate. For decades, human activity has been steadily increasing the concentration of greenhouse gases in our atmosphere, trapping more heat and causing our global thermometer to rise. This isn't just about warmer surface temperatures. It's about fundamentally altering the energy balance that drives all these magnificent wind patterns. One of the most significant changes, a quiet revolution taking place at the top of our world, is known as Arctic amplification. The Arctic region is warming at a rate 2 to 4 times faster than the rest of the planet. Imagine if one end of a great global temperature gradient, like a subtle slope guiding the flow of air, suddenly became less steep. This dramatic warming in the Arctic means that the crucial temperature difference between the poles and the equator is slowly, steadily shrinking. This difference is the very engine, the primary driving force, behind many of our global wind patterns, especially the powerful jet streams. As this temperature gradient weakens, the atmospheric cells themselves begin to respond. We've already seen observations suggesting that the Hadley cells, those equatorial conveyor belts, are expanding poleward. This means the regions of rising warm air are pushing further away from the equator, and with them, the zones of dry, descending air that create our deserts are also shifting. Imagine the subtle boundaries of rainfall and aridity, the very lines that define where certain ecosystems can thrive, slowly migrating. This can lead to drier conditions in regions that once received ample rain and potentially alter agricultural zones, shifting the delicate balance of life that has adapted to these long-standing patterns. But perhaps the most discussed and potentially impactful change is occurring with our jet streams, those swift rivers in the sky. With the reduced temperature contrast between the Arctic and the equator, the jet stream's driving force, its energy, diminishes. This can cause the jet stream to become weaker, slower, and more meandering, less like a straight, fast river, and more like a lazy, winding stream, tracing much larger loops. These exaggerated loops, known as Rossby waves, can cause weather systems to become stuck. When a particular pattern gets locked into place, it can lead to prolonged periods of extreme weather, extended heat waves, persistent droughts, or unusually long cold snaps and heavy rainfall events in specific regions. It's as if the atmospheric shepherd is becoming a bit disoriented, allowing its flocks of weather to linger too long in one place. Furthermore, these shifts aren't confined to the mid-latitudes. The delicate dance of monsoons, the seasonal wind shifts that bring vital rains to billions around the world, are also being affected. As global temperatures rise, the differential heating between land and sea, which drives these vital rain-bearing winds, is altered. This can lead to monsoons that are either more erratic, arriving later, bringing heavier but shorter bursts of rain, or even becoming less reliable overall, creating profound challenges for agriculture and water resources. Even the great ocean currents, deeply intertwined with wind, feel the ripple. The trade winds, for instance, are critical for driving surface ocean currents and influencing phenomena like the El Niño Southern Oscillation, ENSO, a natural climate pattern in the Pacific Ocean that has far-reaching effects on global weather. Changes in the strength and consistency of these trade winds can alter the frequency, intensity, and very nature of El Niño and La Niña events, adding another layer of complexity to our planet's already intricate climate system. In essence, our warming planet is subtly yet surely rewiring its entire atmospheric system. It's like a grand, intricate clockwork mechanism where one gear speeding up and another slowing down changes the timing and precision of the whole device. The result is often an increase in unpredictability and a greater propensity for extreme events, challenging both natural ecosystems and human societies to adapt to a world where the very breath of the earth is taking on a new, unfamiliar cadence. And as these global winds shift and change, sculpting our weather in new ways, we begin to wonder about the more localized, more intimate breezes that touch our lives every day, and how they too might be part of this vast, interconnected transformation. We'll explore that gentle touch of the wind closer to home next. And so, as the day gently folds itself into night, and the world begins its quiet slumber, we pause to remember our tireless companion, the wind. It has traveled far, hasn't it? A silent, invisible dancer pirouetting across continents and oceans, never truly resting, always in motion, guided by the sun's warm embrace and the cool, patient turning of our beautiful earth. Think back to its journey, not as a bustling rush, but as a graceful, unfolding story. We imagine the air, warmed by the sun, rising, light and buoyant, like a soft sigh escaping into the sky. And then, as it cooled, gently descending, finding its path along the ground, a delicate ripple across the landscape. This quiet rising and falling, this subtle seeking of balance, is the heart of the wind's timeless voyage. It's not a struggle, you see, but a natural, peaceful rhythm, as steady and sure as your own breath, as you drift closer to sleep. Recall how it touched the towering mountains, not with a forceful push, but with a respectful caress, flowing around their ancient forms, sometimes gathering strength, sometimes softening to a mere whisper. It visited the vast, shimmering oceans, skipping across the waves, a playful spirit stirring the surface, carrying the scent of salt and distance. From the deepest, bluest parts of the world to the shallow, sun-drenched shores, the wind was there, a quiet witness to the ebb and flow of the tides, a gentle partner to the endless horizon. And it danced through the forests, didn't it? Not tearing, but rustling, a loving hand passing through the leaves, making the branches sway in a slow, hypnotic rhythm. It carried the tiny seeds of life, scattering them with exquisite care. A gardener of the wild, planting future dreams beneath the earth. It sang through the tall grasses, a lullaby for the sleeping creatures, a soft symphony that only the quietest ears could truly hear. In every rustle, every sigh, there was a message of peace, a reminder of the world's continuous, gentle turning. This wind, this invisible breath of our planet, connects everything. The air that touched a distant desert, warm and dry, later cooled and softened as it traveled, eventually becoming the gentle breeze that now whispers at your window. It's a continuous, unbroken thread, weaving together all the moments of our world, from the busiest day to the quietest night. It asks for nothing, demands nothing, yet it is always there, always moving, always sharing its quiet presence. There's a deep comfort in this endless journey, isn't there? A reassurance that even in the greatest expanse, there is a constant, gentle motion, an unseen hand guiding the world. The wind doesn't hurry, it simply is. It doesn't worry, it simply moves. It embodies a beautiful, natural patience, a timeless grace that invites us to slow down, to breathe deeply, and to simply be. As you close your eyes, imagine the wind, now a soft, barely perceptible current in the quiet night. It continues its gentle work, a silent guardian over the sleeping world. It will carry the dreams of one continent to another, whisper secrets of the stars to the trees, and gently guide the morning dew to settle upon the leaves. Its journey is a never-ending story of quiet wonder, a testament to the serene energy that flows through all things. And as you drift into your own dreams, perhaps you'll feel that gentle current too. Perhaps in the peaceful landscape of your slumber, you'll feel the wind's soft touch, carrying you on its own invisible currents, a calming presence guiding you through the night. Rest now, knowing that the world continues its beautiful, peaceful dance, carried on the softest breath of the wind. Sleep well, sweet dreamer. The wind's gentle journey will keep watch until morning. And now, my dear friend, as the day gently folds itself into the quiet embrace of night, let us take a moment to softly close the book on our wondrous journey. We have traversed vast, unseen landscapes, not with hurried steps, but with the gentle curiosity of a whispered thought. We have ventured into the very heart of existence, a realm so intricate, so profound, yet often hidden from our everyday gaze. Remember how we quietly stepped into that world, smaller than a speck of dust, yet teeming with life and purpose? We didn't need a grand telescope or a roaring rocket. Our journey was one of imagination, guided by the soft glow of understanding. We simply let our minds drift, like a feather on a gentle breeze, through the silent, bustling cities of the microcosm. We spoke of the tiny architects, the invisible builders that craft every leaf, every drop of dew, every beat of your own heart. We didn't name all their parts or chart every single pathway, for our purpose was not to memorize, but to marvel. We simply felt the quiet hum of their tireless work, the delicate precision with which they arranged themselves, forming patterns of breathtaking beauty and function. These are the ancient, patient hands that weave the very fabric of reality, a tapestry so fine, so detailed, it can only be truly appreciated with a quiet heart. And then we pause to observe the countless tiny dancers, the unseen inhabitants that flit and swim and glide through every corner of our world, and indeed within ourselves. We didn't need to understand their every move, only to feel the vibrant energy of their collective existence. They are the silent partners in life's grand ballet, each playing a vital, intricate role, contributing to the delicate balance that allows forests to grow tall and oceans to teem with life. Isn't it a comforting thought to know that even in the smallest drop of water, there is a universe of gentle activity, a symphony playing on, unheard by our ears, but felt by our souls? We didn't delve into complex theories or challenging equations. Instead, we simply allowed ourselves to be present with the idea that everything, absolutely everything, is made of these miniature wonders. From the solid ground beneath your feet to the soft air you breathe, from the light of the moon to the warmth of your own skin, it is all a magnificent assembly of the incredibly small. And in this realization, there is a profound sense of interconnectedness, a gentle reminder that we are all woven from the same miraculous threads, part of the same grand unfolding story. This journey wasn't about finding definitive answers, but about nurturing a sense of wonder. It was about feeling the quiet awe that comes from glimpsing the hidden artistry of the universe, knowing that beneath the surface of what we see and touch, there is an entire world of silent, intricate beauty perpetually at work. It's a beauty that doesn't demand attention, but simply is constant and true, a source of endless fascination and peaceful contemplation. As you lie here, nestled in the comfort of your bed, perhaps you can still feel the gentle echo of that tiny world within you. The same wondrous processes, the same delicate balances, the same tireless, invisible work is happening right now, keeping you safe, keeping you warm, keeping you alive. It's a reassuring thought, isn't it? To know that even when you are still, even when you are resting, the microcosm within you continues its gentle, life-sustaining dance. There's no need to grasp it all or to hold on to every detail. The true gift of our journey was simply to open our hearts to the possibility, to allow a quiet sense of marvel to settle within us, to understand that the greatest wonders are often the most subtle, the most unassuming, the ones that whisper their secrets rather than shout them. And now, as your eyelids grow heavy and your breath deepens, allow that feeling of gentle wonder to accompany you. The world, both vast and microscopic, continues its peaceful rhythm. The stars will twinkle, the moon will shine, and the countless tiny wonders will continue their silent, beautiful work, whether we are awake to observe them or not. Let your mind drift, knowing that the journey through the wonders of the microcosm doesn't truly end here. It simply transforms. As you close your eyes, perhaps your dreams will become new landscapes for exploration, new pathways into the unseen, where the tiny architects and the silent dancers will continue their ballet just for you. Sleep now, my dear friend, and may your dreams be filled with the quiet, comforting magic of the universe, both within and without. Good night.